I am Nicolas Tresch. I'm the moderator of this session. So it's a session about economics. It's entitled, How Can Economic Sciences Help Us Make Good Decisions in a Context of Climate Uncertainty? I think this session will show you a sort of an overview of different approach of risk and uncertainty in models of climate policy, in economic models of climate policies. So we will have 5 presentations in 2 parts. First, 2 presentations. After these 2 presentations, we'll have a short time for questions, like 10 minutes. Then we'll have a break, and then we will have another 3 presentations, and again, a short time, maybe 15 minutes, because we have 3 papers for questions. So first session, we have 2 directors, the director of TSC and the director of the Grantham Institute at LSE. So we start with Christian, who is going to talk about long-term risk.
Thank you very much. It's going to be a very interesting morning in a very interesting conference up to now. Today, for my short time, I would like to talk about, how do I do this? No, okay. So I would like to talk about the importance of parametric uncertainty when we need to evaluate long-term project and long-term investment. And so this is related to climate change, of course, because investing in climate change at the same time is a very long-term project. I mean, reducing emission will impact the welfare of future generations for the next 3 centuries, and it's also very risky because we don't really know what will be the intensity of climate change and therefore what will be the marginal benefits of those investments. Okay, so if we want to think about how to value long-term project or long-term investment or action with long-term impacts, I mean, we usually use a standard model, which is the consumption-based capital asset pricing model, in which one of the important ingredients is the assumption of normality. We assume that risks are normally distributed. Okay, and then you get the CAPEP formula, which tells you that in order to evaluate a risky project, you need to discount future cash flows by expected cash flows, in fact, by using a discount rate, which is the sum of 2 components. The first one is the risk-free rate, RF, and the second one is a risk premium. And the risk premium is typically, in this model, with the Gaussian distribution, is proportional to the beta of the project. So you need to evaluate the beta of the project, and you multiply it by a systematic risk premium pi. And then you get, by adding these 2 components, you get the discount rate to be used to evaluate your project. So that's relatively easy. If you know the risk-free rate and if you know the risk premium, you just need to compute, to estimate the beta of your project to determine how to value it. And one of the important difficulties for thinking about climate change, in particular the social cost of carbon, this carbon price that Jean Tirole and I and many others, of course, try to put in place in the context of the international agreement of COP21. One of the important difficulties that most of the literature that has been devoted to estimation of the social cost of carbon has made the implicit assumption that the climate beta, as we call it with Simon, the climate beta, the beta that should be used to determine the discount rate to evaluate the future impact of reduction of emissions today, is implicitly assumed to be 0. And therefore, the debate up to now has been mostly devoted about what should be the risk-free rate to discount the benefits of mitigation. Well, so this discussion about the climate beta, I will mostly put it for the second paper that I wrote jointly with Louis Kessler and Simon Dietz, which will be presented in the second part of this first session. So right now, I will just focus on which risk-free rate and which risk premium we should use in this formula. Okay, and if we think about that, we basically have two difficulties. The first one is, well, the two of them are related to the financial puzzles, and the first one is the risk-free rate puzzle. The risk-free rate puzzle tells us that during the 20th century, when we observe a risk-free rate which was extremely small compared to what we believe as economists, or most economists would believe it should be. So we observe typically between 0 and 1% in real interest rate during the 20th century, whereas the model typically generate a prediction for the risk-free rate between 3 and 4%, I would say. So that implied that during the 20th century, we invested too much, widely too much, in risk-free assets. We accumulate a stock of capital that you can see here today, for example. And that was extremely important accumulation of capital compared to what should have been done if people would have been more rational. And then the second puzzle is the equity premium puzzle, which tells us that in fact, if we invested too much in risk-free assets, we didn't invest much in risky assets because on capital market, we observe an extremely large risk premium between 4 and 6%, whereas a typical CAPM model would predict something like 0.25%. So that implied that we didn't take much risk during the 20th century. So all those things are related, are based on the assumption that we assume that growth will follow a geometric Brownian motion, therefore all risk we face are normally distributed. But if we look at the data, we know that during the 20th century, I mean, the data are not compatible with the normal distribution. We faced during the 20th century extreme events, and those extreme events are not taken into account by most investors. And I mean, no, but at least they are not taken into account in the models that generated those predictions of a relatively large risk-free rate and a relatively low risk premium. And here you have a series of events collected by Robert Barrault and co-authors that were relatively extreme. And so the idea is that maybe if we include those extreme events in the modeling and the way we think we should value a risky project or a project with a long-term impact, maybe that could explain the puzzle, and that would justify using observed price when we need to make a normative recommendation about what to do, for example, in relation to climate change. And the ideas are as follows. If we introduce those extreme events, of course, introducing a fat tails in the distribution in a normal distribution, we imply you increase the risk. And if we increase the risk, people will want to save more. That's the notion of precautionary saving. And if you want to save more, that will affect the impact to reduce the interest rate. And therefore, it goes into the good direction to solve the risk-free rate puzzle. At the same time, if you increase the macroeconomic uncertainty by adding those extreme events in your beliefs, you magnify the long-term risk. And if you magnify the long-term risk, macroeconomic risk, you also magnify the risk of all projects with the non-zero beta. And therefore, you can also explain, I mean, at least it goes into the good direction to explain the equity premium puzzle. So these ideas developed by Robert Barrault and others to introduce extreme events in the standard modelings of the CAPM could explain the two puzzles. And so let me show you a typical representation of this idea by using an approach suggested by Jan Martin in particular from LSE. So let me assume that and that's Barrault typically make that assumption. Let us assume that the future, in the next 200 centuries, and maybe more, every year we will determine the growth of the economy, of the French economy, by taking a draw from a compound lottery. And the compound lottery is as follows. So the first stage of the lottery is with probability 2%, sorry, no, let me start with a simple situation. With the business as usual, so with a probability of 98%, you will be allowed to get a draw from the business as usual earn, where the expected growth rate will be 2.5% and the volatility is 2%. So that's the typical numbers you find when you calibrate the CAPM formula. So assume that on average the growth will be 2.5% and some volatility around this mean. But with a probability of 2%, you will not be allowed to get the draw from the standard earn. You will have to get a draw from a catastrophic earn, where the expected growth will be minus 39%, with an extremely large uncertainty of a volatility or a standard deviation of 25%. Okay, and so every year you will face this big uncertainty. So you have the standard case, a compound normal distribution with the business as usual, and then a potential catastrophic event that can happen on average with a probability of 2%. Okay, so let us recalibrate the CAPM using this specification. If you do that, in fact, Barrow don't use a 2% catastrophe, but he uses a frequency of 1.7%. He used 1.7% because he collected data from from 35 countries for 100 years. So he collected, in fact, 3,500 year countries. And from this data, he observed 60 catastrophes, 60 cases where the annual drop in GDP per capita was larger than 18% or something like that. So, and once you do that, you indeed get a relatively low risk-free rate as an equilibrium. So the model will generate a prediction which is very close to what we observe as the interest rate in the economy, and you also get a very large risk premium of almost 6%. So in a sense, Barrow has been able to explain the observed price in the economy. So the difficulty I have with this representation of the world is for the estimation of this 1.7% probability of facing a catastrophe. So if you remember correctly, I mean, this 1.7% came from the observation of 3,500 events. Some of them, 60 of them, were catastrophes. So if you take a Bayesian approach by having, you ignore at the beginning what's the probability of facing catastrophes, and then you observe those data of catastrophes. In fact, your posterior probability distribution will be a beta distributed. Okay, and here is the distribution of this is the density function of the exposed probability of catastrophes once you observe those data. So in fact, the probability of 1.7% is just an estimation. In fact, in the real world, you don't know what's the frequency of catastrophes you will face for the next 2 centuries. Okay, in fact, it's beta distributed. You have some parametric uncertainty in the model, and I think we should take into account of that. And that's not taken into account by Barrow. So my paper is, in fact, much broader than just examining this special case of parametric uncertainty. In my model, I consider a very general context where you face an IID process for the growth of the economy, but this IID process is characterized by a probability distribution with some parametric uncertainty. So here I assume that you have a mixed normal where you don't know the probability of getting the catastrophic normal, but you could also have a representation where you don't know what is the long-term trend of the economy or what is the volatility of the economy. So what's the consequence? So before going to the result, what's the consequence of recognizing that in the real world, compared to the ideal model examined by most economists, we face deep uncertainty? Okay. The main message of the paper is once you recognize that we face parametric uncertainty, that parametric uncertainty has deep impact on the way we need to think about how to manage and value long-term risk. Okay, that's an important message. Okay, and you will see numbers related to that. In which direction this parametric uncertainty will affect this evaluation process? Well, if you have a risk-free project, if your project is risk-free, it will tend to reduce the discount rate you should use to evaluate this risk-free project. The idea is very simple again. If you introduce this parametric uncertainty into the model, that will not affect much the way you think about the short term, because this parametric uncertainty will, does not play any role. But for the long run, of course, this parametric uncertainty has a deep impact on the way you think about what will be the world in 2 centuries from now. And because you are prudent, you want to do more to help those people who will face this parametric uncertainty. And how can you help those people? You help those people by reducing the discount rate to evaluate those projects, those risk-free projects, which will increase the revenue available for these people. In fact, what I show in the paper is that in this parametric uncertainty, any parametric uncertainty in this modeling will always generate a decreasing term structure for the risk-free rate. So the decreasing term structure for the risk-free rate, it means you want to save more, to invest more in risk-free projects once you recognize that you face a parametric uncertainty. And that's related to the literature on the debate on the discount rate for climate change and on the social cost of carbon initiated by Marty Weitzman and many others. Well, so that's good for environmental economists, okay? This message is, well, standard finance theory is bad. It does not recognize that there are deep uncertainty, parametric uncertainty in the way we model the long-term future, and therefore it should induce us to do more for the distant future. The problem is that that's true for the risk-free rate. Okay, the parametric uncertainty reduces the risk-free rate for long maturities. But at the same time, when you think about that, it also affects the pi. So remember, the discount rate you need to use for a risky project is the sum of the risk-free project plus beta times the risk premium. And the problem is parametric uncertainty, of course, also affects the pi. In which direction does it affect the pi? Well, it tends to increase the pi. Well, why? That's completely trivial. If you introduce this parametric uncertainty, there is so much more uncertainty about what will be the consumption for the generation who will live in 2 centuries. This uncertainty will percolate to the uncertainty affecting the impacts of the cash flows of your investment project that are risky with a non-zero beta, okay? Remember, the beta is the elasticity of the cash flows to a 1% change in GDP per capita in a consumption-based capital asset pricing model. So if you have a certain GDP per capita, you will have uncertain cash flows when the beta is not zero. And therefore, if you introduce more uncertainty about the GDP per capita in 200 years from now, you increase the risk associated to all projects with a non-zero beta. So that generates, because of risk aversion, that generates a larger risk premium. So in fact, in parametric uncertainty, whatever parametric uncertainty you consider, this parametric uncertainty will positively impact the risk premium, and therefore, in fact, you have an increasing term structure for the risk premium. Okay, here is an illustration of the consequence of taking into account this parametric uncertainty in the Barro's model. So remember, I think in the Barro model, Barro assumed that with probability 2%, 1.7%, there will be a catastrophe, a macroeconomic catastrophe next year in France. Well, this 1.7% is only an approximation, it's an estimation, but we need to take into account the uncertainty affecting this probability. It should impact the term structure of the risk-free rate of the risk premium by increasing the long-term risk premium, by reducing the risk-free rate. By how much? Well, remember, without taking into account the parametric uncertainty, you have those numbers, that's the Barrow numbers, and that should be the risk-free rate and the risk premium that should be used whatever the maturity you consider. But once you consider this, once you introduce this parametric uncertainty, you get crazy numbers. The asymptotic value of the risk-free rate will be minus 203% per year. And the risk premium will be plus 63% per year. So you see, there is some kind of overshooting in Barrow's model, to say the least, once you recognize this parametric uncertainty. So here the message is not only quantitative, it's also qualitative. I would like to convey the message that in most risk valuation, in most models used today by people in finance and finance theory, and recognizing that there is parametric uncertainty in most of the parameters of the model, and that's not very important for the short run. But if you really need to use the same kind of tools to evaluate projects with very long-term benefits and costs, you need to really think about the consequence of parametric uncertainty, and that's just an illustration. So I will not go into the details of the model. The model is completely standard. It's a normative model where I have a representative agent who is risk-averse. You derive from that consumption-based capital asset pricing model rules for computing the risk-free rate and the risk premium. So that's completely standard model. The only thing new is in the calibration of those equations, I recognize that the stochastic process governing the CT has some parametric uncertainty. And the main result of this model is that this parametric uncertainty will not affect the short-term risk-free rate, will not affect the short-term risk premium. So parametric uncertainty has no role to play when we think about the short term. And that's probably why people in finance were not very much concerned until recently about parametric uncertainty. But this parametric uncertainty has the effect to generate a decreasing term structure for the risk-free rate. So has potentially a deep impact on reducing the risk-free rate for the long run. And at the same time, it generates an increasing term structure for the risk premium. Okay, just because I get short on time, just another application of the same model, okay? And just let me illustrate this with this picture. So in the application I just presented in the introduction, most of this presentation, in fact, there was some parametric uncertainty on the probability of a catastrophe. Here, I take a much simpler approach where you know that you face a geometric Brownian motion for the growth of the economy for the next millennium. But the problem is you don't know what's the drift, what's the mu of the geometric Brownian motion. It's not necessarily 2%. It could be, in fact, in this model, I assume that, so I know the volatility of the growth rate. So the volatility of the Brownian motion is known, it's 4%. But the drift of the economy is, you don't know, it's a constant, but you don't know what constant it is. You will learn in the future what will be the trend, because you will just observe year after year what will be the growth of the economy, and therefore you will update your belief using Bayesian rule. But in the short run, you don't know what it is. And your belief is currently represented by a uniform distribution between 0 and 3%. So average of 1.5%, so that's relatively comfortable. In expectation, the future generation will be much wealthier than us, and we should not care too much a priori about what will be their welfare, and the climate change will be mostly on their head, not on ours. Well, it's not so important because those people will be so much wealthy in expectation. However, taking into account of this parametric uncertainty on the mean rather than on the probability of a catastrophe, I get 0. I believe I still have 3 minutes. Okay, I see. So here is the result. So forgot to mention, I typically use in my modeling constant relative risk aversion of 2. And so that's the term structure you get in this calibration of the model, so between 0 and 400 years. Think about climate change. Here is the term structure of the risk-free rate, beta equals 0. The risk-free rate becomes around start from 3% and go down to, in fact, to 0% in the very distant, for the very distant maturity, for very young maturities. But if you take a project whose beta is equal, for example, to 1, you should use a constant risk premium, a constant discount rate, risk-adjusted of 3.5%, something like that. So you see that the two effects for a beta equal 1 project, the two effects of a decreasing risk-free rate and increasing risk premium compensate each other perfectly. And in fact, it's a theoretical result. That when beta is equal to gamma divided by 2, you get a flat term structure. Okay, here is the situation where you also take into account of business cycle in the modeling by using a mean reversion, long-run risk, Banzali-Aron kind of modeling. Let me just finish, let me use my last minutes to introduce the next paper. So then the last question we need to think about when we have to determine the problem of evaluating climate change investment is what's the beta of any investment in which you marginally reduce the emissions of CO2 in the atmosphere. Well, and here is my last slide. And that's, again, an introduction for the next paper. In fact, there is much uncertainty about what is the climate beta. And so that's why we joined force with Simon and Louise to try to push the literature into that direction. We believe it's crucial. So there is a negative beta story. So remember, the question is, do we think that we fight climate change because most of the impact of climate change will happen when GDP will be very low? So a negative beta, okay? If investing in reducing climate change emission generate most of the benefits when the future generations are very poor, well, that's an additional incentive to fight climate change, okay? Negative beta, there is this investing in that kind of project provide an additional edge of the macroeconomic risk. And so the discount rate should take into account of that. We should reduce the discount rate. And there is a simple argument for why that may be true. Well, of course, if we believe that most of the uncertainty faced by the future generations is climate uncertainty, climate sensitivity, by how much average temperature is increased when you double the concentration of CO2 in the atmosphere, then you, of course, if the sensitivity happens to be large, climate change impact will be large, temperature will explode, consumption will be very small, and at the same time, today, reducing emission will have a large marginal benefits for those people. So that's a negative beta story. The problem is that, as Simon will show you, there is another story, and that other story is the dominating story. What's that story? The dominating story is, suppose that most of the uncertainty faced by the future generation is about by how much what will be the growth rate of the economy. Okay, so the macro exogenous uncertainty that would come from innovation or non-innovation, diseases, and things like that. So independent of climate change. Then, if the scenario is good with a large growth rate of the economy for the next 2 centuries, consumption will be large. In the business as usual, emission will be large. Therefore, concentration will be large. And because we believe that the damage function is convex, the marginal benefits, because I will be to the right of the diagram, the marginal benefits of reducing emission will be large in a world where consumption will be large. So you have a positive correlation between consumption and the cash flows of your investment today, and therefore the beta is positive. Symmetrically, if you believe that if the scenario is low consumption, low emission, low concentration, marginal benefit of reducing emission will be small, and therefore small consumption, small benefits. So most of the benefits are realized when everything is okay. So climate change is not a big deal because most of the damage will occur when people will easily face the problem because they will be very wealthy. That's a positive beta story, and it happens that when you calibrate standard model, like the Nordos model, and that's Simon's work, you will see that the beta is positive and quite large. Thank you very much.
Okay.
C'est celle-là.
Okay, good morning, everyone. Bonjour. It's a pleasure to be here. And, well, Christian has done an excellent job of in motivating this paper that I'm going to talk about now, which is joint work with him and with Louise Kessler, who is also here today in the audience. In a nutshell, the purpose of the research that I'm going to report to you is to ask the question, does mitigation of climate change, in other words, reducing carbon dioxide emissions, increase or decrease the aggregate consumption risk faced by future generations? Consumption in the sense of our spending on all goods and services. An economist's typical measure of how well off we are at a point in time. And if you think about this question in the context of the standard capital asset pricing model that we use in financial economics and finance, then another way to ask the question is to say, what is the climate beta? What is the elasticity of climate damages or the benefits of reducing carbon dioxide emissions with respect to a change in aggregate consumption? Do benefits go up when consumption goes up, in which case beta is positive, or is the opposite the case? And people have thought about this issue before, of course. Our added value is to provide, as far as I know, what are the first estimates of the climate beta from a so-called IAM, in other words, an integrated assessment model. These are the models that economists build to do cost-benefit type calculations around climate change. And to do this, we take certainly the most famous and probably the best integrated assessment model, Bill Nordhaus's DICE model, which, however, is usually a model which doesn't explicitly deal with risk and stochasticity, although sometimes it's been set up to do that. And we try to do a really careful calibration of most of the, or all of the important sources of uncertainty relating to climate change and its impacts and interactions with the economy. And you know, much of the claim that we can make to the importance of the results of this paper will depend on how well we do that calibration of uncertainty. And as Christian alluded to, we find that the climate beta is approximately 1, and that this is, in a sense, robust to the time period, meaning that holds not only in the near future, but over the whole of the next 2 centuries or so. And it's also robust to implementing a reduction in carbon dioxide emissions at the margin on 2 radically different kinds of emissions scenario. And the reason for that is that of all the contributing factors to uncertainty about future consumption due to climate change, the contributing factors to the beta, the overwhelmingly important one is growth in the productivity of the economy. Why do we care about the climate beta? Well, I don't need to say too much about that because Christian has already mentioned it. But basically, one way to look at this is to say it plugs into the discounting controversy, the controversy over the appropriate discount rate, social discount rate to use for climate change. One element of this controversy, and perhaps a rather overlooked element of the controversy, because as Christian said, most people have had arguments about the risk-free rate and its parameterization. But one element of this is that if emissions abatement has a positive beta, if it increases the consumption risk faced by future generations, then the social discount rate should have a risk premium on it to reflect the fact that reducing carbon emissions is increasing the risk that we face in the future. And the opposite would be the case if the beta were negative. It would have this so-called insurance value. And as I said, I think this is one of the main issues left over from the debate after the publication of the Stern Review in 2006 on the economics of climate change about the appropriate discount rate for climate change. As Martin Weitzman from Harvard wrote a very interesting review of the Stern Review in the Journal of Economic Literature in 2007. And part of that paper was to say that, well, we're having arguments about whether the risk-free rate or the rate of return on risky assets in the economy is a more relevant benchmark for our thinking about the social discount rate to use for climate change. And actually, which one of these turns out to be more compelling depends in large measure on whether the benefits of reducing carbon emissions are correlated with growth of the economy. In other words, whether there's a positive beta or not, or a negative one indeed. And of course, when you start to get into this territory, you also get into the territory of the good old asset return puzzles, the risk-free rate puzzle and the equity premium puzzle. And as you'll see later in the talk, I will not be able to steer clear or completely avoid those asset return puzzles either. So previous literature, I don't think for this audience I need to go through this in great detail. Just to say that there have been a few contributions in recent years thinking about the climate beta. None of them, well, several of them offer, I think what is fair to say is a partial take on the problem by constructing a simple model and looking at just one of the possible sources of positive or negative values for the beta. A paper in Environmental and Resource Economics in 2007, which by only looking at uncertainty about the damages from climate change suggested that beta would be negative and that mitigation would have insurance value. A story that Martin Weitzman has also been telling, but not working in the capital asset pricing framework. And then the paper that Christian described, where he suggests that actually if we think about uncertainty pertaining to productivity growth, then beta, we expect it to be positive. So I have a few slides on beta. They're a bit technical, so I propose to just zoom through these. You'll see a bunch of equations. I suggest you just ignore the large majority of them, and I'll show you what I want you to pay attention to. So it's a standard economic model. And under the assumption that we are doing a small or marginal project, something that won't affect the future consequences of for the economy, well, not in a large way anyway, then we can work out whether a particular project improves or decreases welfare by just calculating the project's net present value worked out as the sum of discounted cash flows, essentially, discounted at a risk-adjusted rate R sub t. And if you make a series of other technical assumptions, you get to this equation that Christian also showed, which says that the risk-adjusted rate to apply to the project is equal to the risk-free rate plus the product of the systematic risk premium pi and the beta. And moreover, in this setup, the beta itself is simply the coefficient of a simple linear regression equation of the benefits B of reducing carbon dioxide emissions on consumption per capita in the economy as a whole. Okay? So that's all I really need to say about the basic theory, except one thing, which is hopefully at an early stage going to head off a potential source of misunderstanding of what our results of positive beta mean for our willingness to take action on climate change. And here's the wrinkle. So although a positive and large beta implies we should be applying a higher discount rate to the benefits of reducing carbon dioxide emissions, having a positive beta also raises the expected cash flow, the expected benefits of action on climate change, and you can show this just by decomposing expected benefits, the flow of money returns from reducing carbon dioxide emissions, into the product of a couple of terms, initial consumption and growth in consumption, both of which depend positively on the beta. From this, you can derive a condition which brings together the discounting story and this cash flow story and tells you under what circumstances will a positive climate beta actually increase the value today of reducing greenhouse gas emissions. And this is the condition. It says that as long as the beta is larger than the risk aversion coefficient minus the ratio of mean consumption growth over the variance of consumption growth, then this will be true. And if we, for instance, just look at data from the United States for the last century, where mean consumption growth was about 2%, and the standard deviation was about 4%, and if we take a fairly standard value for the coefficient of relative risk aversion, then the right-hand side of this inequality has a value of about minus 10.5, and clearly for any sensible value of beta that we're talking about, including a positive value, this condition will be met, meaning that we are in fact saying at the end of this whole exercise that if you take into account the climate beta, then in fact our willingness to pay to reduce greenhouse gas emissions is larger, not smaller, despite the fact that the discount rate that we should apply to climate mitigation attracts a risk premium for the reason of this positive beta. Now, a little bit for a few minutes about the actual modelling that we did. So the DICE model is a model that has about 50 parameters that you could randomize. But actually, not all of them are relevant to this exercise. Some of these are preference parameters, and we're only interested in estimating consumption. And other parameters have been shown to not be terribly important overall in uncertainty analyses. So we keep focusing our attention on 7 issues or 8 parameters of importance to the results. And these really deal with every step in the chain linking carbon dioxide emissions with climate change and damages. We look at uncertainty in economy-wide productivity, uncertainty in the size of the future global population, uncertainty in the rate at which the economy will autonomously decarbonize. In other words, how much less carbon intensive will the global economy become even if we don't make efforts to reduce emissions through applying policies. The cost of reducing carbon dioxide emissions, the way in which the carbon cycle works, the way in which carbon dioxide transfers between the atmosphere and the oceans, so a physical uncertainty. The infamous climate sensitivity, or essentially how hot the planet gets in response to an increase in the atmospheric concentration of greenhouse gases. and two aspects related to our understanding of damages, in other words, the economic impacts of climate change as a function of warming. For each of these uncertainties, as I said, we really tried to make a careful effort to calibrate the uncertainties based on the evidence. Now, I don't want to go into detail on each of these uncertainties, but I do want to talk about 4 of them, because I think that will be helpful in understanding the results. And the 4 I want to talk about in a little more detail are productivity uncertainty. I want to talk about the rate of decarbonisation because it's a good way to explain to you why in a dynamic model like DICE, the effect of these parameters on beta is not as straightforward as you might think. That's why in many cases we cannot say unambiguously what the effect of uncertainty in these parameters is going to be on the beta. Thirdly, I want to say a bit about climate sensitivity, and lastly, I want to say a little bit about damages. So let me move forward now and do that. So productivity growth. Now, we've known for quite some time that uncertainty about so-called total factor productivity is very significant in understanding the output of integrated assessment models. In fact, there's a paper by David Kelly and Charlie Kolstad from nearly 15 years ago which showed this. So it didn't come as a surprise to me that when we put this into the model, that in fact this turned out to be ultimately the key driving force. And as Christian explained, this is one of the parameters for which you can say that the effect on beta is unambiguous and it's positive. And the reason for that is that if you have an economy for which productivity is growing rapidly, that's an economy in which output is growing rapidly, and consumption is growing rapidly, so we're rich, but it's also, given that carbon dioxide emissions are a byproduct of economic activity, it's a world producing a lot of carbon, a world with a lot of carbon in the atmosphere, a hot world, and a world with large damages, both absolutely and relatively, assuming the damage function is convex. So marginal damages are large, so benefits are large, and consumption is large. And of course, in a model which tries to make forecasts over a couple of hundred years, and that's what integrated assessment models do, we need to try to calibrate the uncertainty using a very long-run data set. So with the help of a couple of colleagues at LSE, we collected nearly 200 years of data on productivity growth in the United States and the United Kingdom, and we put a probability distribution over that. So, and this is what the data looks like. So this is, in models like this, you're talking about long-term productivity trends. You don't want to be estimating this coefficient and picking up business cycle effects. So this is a rolling 30-year average of productivity growth in the US and the UK, estimated using standard growth accounting approaches. And you'll see that, in fact, a normal distribution fits this data very well. It fits it better than for a fat-tailed example distribution, which is a logistic distribution. Now, to say something about so-called autonomous decarbonisation. So what is this? This is the idea that, and this is an empirically demonstrated fact, that over time, structural change in the economy, away from primary and secondary industries towards services, as well as technological improvements in any given sector, make us less carbon intensive. So we will become less carbon intensive, even if we don't work to introduce climate change policies. The question is how much. Okay? Now, the reason that I bring up autonomous decarbonisation in my talk is that it actually, like many of the parameters in DICE, it has an ambiguous effect on the beta, although we could say it's probably positive. Why? Well, start by thinking about a given trajectory for the economy. If the rate of economic growth is given, then if we have a faster rate of autonomous decarbonisation, that's just a good thing, right? That means we can grow with a lower climate change cost. Consumption will be higher, the damages from climate change will be lower, marginal damages will be lower, and the benefits of reducing carbon dioxide emissions will be lower. However, in a dynamic model like DICE, the path of output is not given. Okay? Lower damages means higher income at a point in time. Higher income means you have more money to invest. If you have more money to invest, then the path of future consumption can be higher. It's not given. Consequently, we can't say unambiguously that if the rate of autonomous decarbonisation increases, then marginal benefits will go down. There is a countervailing effect through investment. But that countervailing effect through investment is probably not very large, and consequently, the effect on beta is probably positive. Climate sensitivity, I'll just skip through this relatively quickly. As I said, this is how hot the world gets as a result in increasing the atmospheric concentration of greenhouse gases. It's widely recognized to be a key physical uncertainty in climate change, maybe the key uncertainty. It likely has a negative effect on beta, and this is a story that Christian explained in his talk. If you have a high climate sensitivity, it means higher damages, which should mean lower consumption and higher marginal benefits of mitigation. But of course, there is this investment effect which might go against this, at least to some extent. This is our fit of the IPCC's consensus statement on the climate sensitivity from its 2013-14 report. And you can see, as is probably well known now, that it has a so-called fat tail. Right? It has a long tail of high values. And many people argue that this is what we're really worried about when we're thinking about climate change. Not this region so much, but this region here. The possibility that the planet might warm up by 6, 7, 8, 10 degrees as a result of doubling atmospheric carbon. Damages. So, as Bob Pindick will most likely tell you later, any insightful discussion of damage functions in IAMs begins with this observation. They are essentially made up. The damage function in an integrated assessment model is key. If you don't have one, you don't close the loop between the effect of the economy on the climate and the effect of the climate back on the economy again. But we don't know very much about damages, in large measure because although we have some data points to constrain the damage function in an IAM for, say, 2 degrees of warming, we have various studies that we can try to fit a curve through. After that point, we don't know anything really. So it could go up, it could go down, it could do really whatever you want it to do. In our version of DICE, we have a damage function which takes a fairly standard form, and it has a linear, a quadratic, and then this higher order term. And what we're trying to do with this is, through the alpha 2 term, we're trying to capture uncertainty about damages from 2 to 3 degrees warming, where we have various data points and we can kind of fit a distribution over them. But with the alpha 3, what we're trying to do is capture differences in researchers', let's call them subjective beliefs about how significant damages could be as a result of larger temperature increases. And this chart is not terribly easy to see, but this tries to show you our state of knowledge about damages and the data points and our approach. So the blue dots are the data points that we have. According to Richard Toll, we have something of the order of 16 independent estimates of the total cost of climate change for a given temperature. Okay, there are many studies, but most of them, in his view, are not independent. So we have 16 independent estimates, and they're mostly around 2 to 3 degrees. Thereafter, there are people like Bill Nordhaus, who effectively argue that damages from climate change will rise modestly. And there are people like Martin Weitzman who have suggested that damages will rise eventually precipitously. Our approach is going to be to fit through the alpha 3 parameter, we're going to basically fit a distribution over the spectrum of opinion. Okay. So let me show you the results, because I only have a couple of minutes left. So this is our estimate of the term structure of beta on a baseline emission scenario. And if you look closely at the axis, you will see that it is approximately 1 throughout. It falls somewhat from a high of about 1.15 to about 0.85. We repeat the exercise on a different emissions scenario because, of course, you wouldn't necessarily expect marginal damages to be the same on very different emissions scenarios. So this is a 2 degrees emissions scenario where we also find that beta is in the vicinity of 1, but it does not fall as far. And of course, the reason for that is quite simply that on a scenario where there are deep cuts in greenhouse gas emissions to try to keep the temperature under 2 degrees, the effects of climate sensitivity and damages, which tend to produce negative betas, are attenuated. Now, we did some analysis of the determinants of the term structure of beta. I'll skip through that to show you one slide. So what we did was we repeated the exercise of taking one of the parameters out of our modelling to see what the beta is with the remaining 7 parameters. And in 7 out of 8 cases, when we took a parameter out and redid the analysis, we found the results looked almost identical, except when we take out the productivity uncertainty parameter. If you do that, then you see how eventually the beta becomes negative and significantly negative in the next century, having removed the effect of productivity growth. And that is a fairly concise way of getting across the fact that our results are due in large measure to the effect of productivity growth. So I'll just say a couple of quick words of conclusion. We find that the climate beta is approximately 1 under various circumstances. This is overwhelmingly due to uncertainty about economy-wide technical progress. Uncertainty about climate sensitivity and damages provides a countervailing effect, but it's not enough. Thank you.
Thank you very much. So we have a few minutes for questions. Yes.
Just Simon, just one point about the damage function. You mentioned Richard Toll's survey, and you said that there were estimates of what the damages are for 2 degrees, but those are not estimates; those are opinions. There's no estimate of what damages are at 2 degrees. We haven't experienced 2 degrees. There's no data, and those opinions, they're fine. They're opinions, but they're no different than the opinions about 7 degrees or 8 degrees.
Yeah, I kind of agree with that to a point. I think that there are degrees of opinion. I do think that what Richard provides in the work that Richard summarises contains some data, whereas, for instance, Martin Weitzman's paper is just a thought experiment in the true sense of the word. But I'm very sympathetic to your point of view about the validity of these data or their reliability in thinking about future climate impacts.
May I add something? Well, that raises a deeper question, which is, what do we do when we don't know the cash flows, even the distribution of the cash flows? I have a lot to say about that, but that will be for another talk.
Two quick questions, Christian. When, I don't know the work of Barrow, but in the 60, what you call catastrophes, out of the 3,500, I mean, that's a drop of GDP. Do you know if any of those catastrophes could be related to a natural catastrophe, such as floods or quake or whatever? Just to see if there is a correlation between what you call a catastrophe and eventually...
I did never look in details on that. Most of those catastrophes come from wars and financial crises.
Okay, so nothing to do with...
Well, it's easy to check. It's an appendix of Barro's paper.
I will look at it. And my second question, all the investments that we have to do in order to fight against global warming, what's the effect on long-term productivity? Because here you have a kind of... for me, I mean, you cannot ignore the fact that, the massive investments we will have to do in the energy fields, in the electricity field, in the energy field, transportation field. It seems there is a kind of built-in effect where those investments could affect long-term productivity.
So we don't, I don't raise the question in my paper. I just look at how to evaluate projects. It could be anything. And also it's marginal project. It's very important. I forgot to mention that. All the things we do are using models to estimate prices in a reference model. So if you use prices, it means that you are a marginalist approach. You just look at marginal project. I think your question is also related to the fact that we probably have to invest non-marginally in different new technologies, and that will generate a new view about what will be the growth of the economy for the next 2 centuries, because we will maybe be more relaxed related to climate change, and that affect the discount rate at which we should evaluate those projects. So it's we should go to a general economic model where you specify the technologies and the production functions. That's not done, and that's probably infeasible at this stage, I think.
I have a policy question. Okay. Who will use your beta? I don't think the private market will change its beta, and I don't think the government will regulate the beta in the economy. So how we can use your result to improve the
Well, it's a normative model. Huh? We cannot observe price of carbon on markets today because it's an externality. Huh? So government are asking economists, how should we price carbon? And behind this question is, how should we value investment that generate benefit for the distant future? Some of them are risky, and so we are asked as experts to provide an answer in a second best world, so where prices are not necessarily the good signals to decentralize an efficient allocation. And therefore, we provide a normative answer to this normative question, which is, what should be the price we should use if we want to improve the world? But you are right, people in the real world don't use social cost of carbon today, and they potentially use a discounting system, which is not the first best discounting system.
Hi, I have a question for Simon. Actually, I have 2 questions. I'm not totally in sort of the theoretical part you were talking about, and that's why I'm trying to make sense of one of the conditions you sort of mentioned, that was the condition on the NVP being positive by looking at US data, and you come up with sort of the condition turning out for typical sort of values to be minus 10.5 for the beta. So can you sort of comment on what that implies? And my second question was, on the uncertainty calibration, you actually taken US and UK data to actually do the uncertainty calibration. Another sort of kind of comment from you on sort of understanding that, is that sort of a bias towards looking only at certain parts of the global economy to actually sort of make the estimation of what is a global investment really to the benefit of the global economy, rather than sort of having a bias towards the UK and the US?
Sure. Yeah. So the first question. So Beta affects the net present value of reducing carbon dioxide emissions at the margin in two ways. It affects the discount rate on the cash flow, but it also affects the cash flow. So expected cash flow. Thank you. A positive beta means a higher risk-adjusted discount rate, but it also means a higher expected cash flow. And the condition that I showed you was the condition for the latter effect outweighing the former effect, basically, and saying that the net present value is larger overall as a result of positive beta. Okay. The second point is a good point, and we could potentially use global data to calibrate productivity uncertainty. I think the reason for going to US and UK data is basically wanting to look at the very, very long run. You want to go back that far, 2 centuries, which is how far forward we're trying to forecast. Then you're basically reliant on Angus Madison's work, a famous economic historian, and the most reliable data for productivity, which nonetheless we still have to estimate indirectly, is for the United States and the United Kingdom. Okay. So that's the reason for using that data.
Okay, last quick questions. Okay.
I certainly like your goal of finding this beta, because I think it has a lot of significance for the discount rate, which has significance for lots of things. But I'm a little concerned with using the DICE model as a way of obtaining it. Two reasons, and you probably already have listed 10 of your own that are problems with the DICE model. But one of them is you're doing a Monte Carlo with each run is just a deterministic model. It's not there's no uncertainty really in the model. But more of a problem, I think, is that the structure of the DICE model, by its very nature, damage goes up with income for the same temperature. 2-degree temperature change, damage scales linearly with GDP. So isn't the assumption basically such that you're going to get the positive beta, and so it's built into the way structure of the model. The beta is built into it.
So this is something that it's a good question, a good point, and something that we're working on right now. We've had various comments on the paper. One of them, which is not correct, is to say that you cannot get a negative beta in a model with multiplicative damages. Clearly, you can do that, and we showed you that it can be done, for example, when productivity growth uncertainty is taken out. Nonetheless, I think there's clearly a sense, and I think that it is possible to show this in a much simpler analytical model, that if damages were additive instead of multiplicative, then the effect of productivity uncertainty on positive beta would be much attenuated. Okay, so basically I'm agreeing with you. But when I start reasoning down that line, I eventually get to the point of saying, well, okay, but which do I find more compelling, multiplicative or additive damages? And I tend to find multiplicative damages a more compelling story than additive damages. So therefore, I tend to think that the results are okay in that sense. But it is vulnerable to that assumption. It's not robust to that assumption, for sure.
Okay, thank you very much, Christian and Simon. And we're back in about 20 minutes for the follow-up studies about economics of risk and uncertainty.